So, welcome to yet another lecture of Machine Learning Foundations course. We are in week 4 and this is the second lecture, and we'll begin the discussion with some core linear algebra concepts here. In particular, the most important concept, that's eigenvalue, and also something associated with an eigenvalue, which is eigenvector. So, we'll understand eigenvalues and eigenvectors for a given matrix. We'll first in this course start with a brief motivation on the which illustrate the need for this concept of eigenvalues and eigenvectors, and then we'll define concretely what for a given matrix what is an eigenvalue and what is an eigenvector, and then we'll look at a procedure to calculate these for a given matrix, calculate all eigenvalues and eigenvectors in this lecture. We'll start the discussion with eigenvalues and eigenvectors, and then cover a lot of topics which build on this, which is looking at real symmetric matrices and trying to look at eigenvalue decomposition and also singular value decomposition, which is a further step from there. And finally, we will end with principal component analysis. That is the plan for this module, which is linear algebra, module 3. We will start more basic. We will try to understand what eigenvalues and eigenvectors. And before I do that, I will start with a motivation. Why do we care about eigenvalues and eigenvectors? The motivation I am going to use is ordinary differential equations. So, imagine you have a equation like this: dv by dt equals 4 times v minus 5 times w, with the initial condition v equals 8 at t equals 0, and add in the other equation. The second equation is du by dt equals say 2v minus 3w, and with the following initial condition: w equals 5 at t equals 0. So, if I use in compact notation, imagine v and w. I think v and w is better. Yeah, this is w. And so, u is in compact notation, say v and w. It is a vector parameter, 2-dimensional, and u of 0 is just whatever v of 0 is. V of 0 is 8 and 5. Now, given this, I can write this equation star. Let me call this equation star. So, star can be rewritten as du by dt equals au, where A is the matrix of coefficients, say 4 minus 5, 2 comma minus 3, and u 0 at t equals 0. That is the initial condition. Now, you want to solve a ordinary differential equation like this, and the solution of such equations leads naturally to eigenvalues and eigenvectors. And we have, we'll look at a very simple case. Consider a very simple case. You just have one equation, simple case of a single equation. So, I just have du by dt equals a times u, and a solution would be u of t equals e power a t into u of 0. So, you can substitute this solution and see that it satisfies. So, let me call this if you double star. Yeah, it is easy to check, easy to see that this solution, this is This is a solution of double star. Now, one is really concerned with stability. This is beyond the topic of this course, but usually one cares about stability notions of this. So, star is unstable if A is greater than 0, simply because e power a t goes to infinity with t. Yeah. Now, star is, it's called neutrally stable. This is not really needed for this course, but just, and the third case is stable. This is the most interesting case if a is less than 0. Yeah, because the solution, it goes to a constant. Yeah, because e power a t becomes, yeah, constant in that. Now, let us look at the case of a 2D parameter. So, if I want to figure out a solutions, if I want solutions of this form, which is say v of t equals say e power minus lambda t into y, and say w of t of the following form for the system star, which I outlined above. Yeah. Or if I write it in the form of the vector parameter, I want this to be e power minus lambda t into x, where x is just y and z. Now, if we substitute this in du by dt equals au, we obtain, we get, you just substitute in the two equations that I had before, which is, so lambda e power minus lambda t y equals 4 e power lambda t y minus 5 e power lambda t z e power minus t z equals the two equations that I had in v and w. Yeah. Now, if you take out e power minus lambda t, we get the very important equation, that is now this equation is the same as a x equals lambda x, and this is the eigenvalue equation. I mean, solving a linear system in an ordinary differential equation context comes down to solving a eigenvalue equation. Here lambda is the eigenvalue, and we want a eigenvector which is non-trivial. This is non-trivial, so it should not be 0. X not equal to 0. So, the message is, I can solve du by dt equals au using solutions of the form whatever I had here, t equals e power minus lambda t x if Ax equals lambda x can be solved. Okay, so that's really the message, and this leads naturally to the definition of eigenvalues and eigenvectors. So, to summarize, I can solve solution of a linear systems of ordinary differential equations is really tied to solving a eigenvalue equation, and if I can solve this, then I can find a solution of the form that I have here, which is here. I can solve an equation with the solution of this form. I can solve an ODE with the solution of this form if I can solve Ax equals lambda x to obtain a non-trivial x. So, that leads to eigenvalues and eigenvectors. Definition. For a matrix A, lambda is a eigenvalue and x is a eigenvector if Ax equals lambda x. So, this is the eigen equation. So, geometrically, if x is here, if this is x, then Ax. So, if x is an eigenvector, then if x is an eigenvector, then A either stretches it or shrinks it, but A does not change the direction of x. So, that is eigenvalue and eigenvector definition. We can look at a special case. Now, if you take the case lambda equals 0, then Ax equals 0 implies where does x reside? X belongs to the null space of A. So, that is the simplest example that you could think of. Now, we will look at a few more examples, and directly just by eyeballing you can calculate the eigenvalues and eigenvectors, at least the eigenvalues. So, the first example, here is a matrix. Projection matrix is something that we saw in the previous module. Let us call this P. For example, project onto a plane. Imagine you project onto a plane. Okay. So, take any vector x, and then P x will be here. It's a right angle which I am struggling to do. Okay, let me put it in that. Yeah. Now, for this I would recommend you pause the video and think about the eigenvalues of this matrix and even the eigenvectors. Strongly encouraged to understand what are the possible eigenvalues and eigenvectors of this projection matrix. In this very simplest case, think of projection onto a plane, which is illustrated here. I am going to go on and give out the answers. So, you can see that P x equals x for any x in the plane. That implies lambda equals 1 is an eigenvalue and any x in the plane is an eigenvector. Now, what about that would be the first one. What about the second one? Is there another eigenvalue? The answer is yes. Consider an x that is, okay, let me just write this as yeah, okay, so this is x is fine, x that is perpendicular to the plane. Then what would happen to px? If x is already perpendicular to the plane, the only projection is 0. So, lambda equals 0 is another eigenvalue, and any x perpendicular to the plane is an eigenvector. So, that is the first example. Let us look at another example. This is permutation matrix. A permutation matrix is, by definition, it's, so what you do is take the identity matrix and shuffle its rows. For example, 0 1 1 0. This is a permutation matrix. Now again pause this video and try to figure the eigenvalue and eigenvectors of this. I am going to give out one example. So, bx equals x. Try to find an x such that bx equals x. Answer is x is 1 1. The second is bx equals minus x for what? Can pause and try to figure this. I have given you the eigenvalue already. The answer is x equals 1 comma minus 1. So, by just these are very simple matrices. So, you can just eyeball and find the eigenvalues and guess the eigenvectors. I mean, but there is a more systematic procedure to doing this, finding the eigenvalues. And the procedure to adopt for this is the following. So, let us start with the eigen equation. So, you have Ax equals lambda x, which is equal to A minus lambda I x equals 0, which is equivalent to saying A minus lambda I is singular, which finally leads to determinant of A minus lambda I equals 0. And this particular equation, when you write down, this is called a characteristic polynomial of a matrix A. Now, if A is n cross n, then the characteristic polynomial is of degree n, and I can write it as some A11 minus lambda into A n minus lambda equals 0. That would be how the characteristic polynomial. The n roots of characteristic polynomial, the roots of this equation are the eigenvalues. So that's how you find. Now that answers one part of the problem. How do you find the eigenvector? We saw that you know, you are trying to find an x such that a minus lambda I equals x. So for eigenvectors want, so if you are given a lambda, want a minus lambda I of x equals 0, that is x belongs to the null space of a minus lambda I. Okay. So find this to obtain an eigenvector corresponding to eigenvalue lambda. So that's really the scheme, and so can use Gaussian elimination. Can use Gaussian elimination to solve a minus lambda I x equals 0. So let's do an example. So suppose A is 3 1 1 3. So I would recommend pause the video, calculate the eigenvalues eigenvectors, and then check the lecture to see if you have done the right thing. So if I do determinant of a minus lambda equals 0, then that is lambda square minus 6 lambda plus 8 equals 0, which is saying lambda 1 plus lambda 2 equals 6 into lambda 2 equals 8. You can verify, check. Lambda 1 plus lambda 2 is called the trace. It's the trace of A. This is the trace of A is equal to sum of diagonal entries. This is true in general, and lambda 1 into lambda 2 is the determinant of A. This is something you can check. Yeah. So 3 plus 3 is the diagonal sum. That is the same as the sum of two eigenvalues, and so on. Anyway, so the eigenvalues are for this. So the eigenvalues are lambda 1 equals 4, lambda 2 equals 2. Now I need to find the eigenvectors. So I will look at A minus 4i, and that turns out to be, subtracting 4 from the diagonal, and that would be minus 1, 1, 1 and minus 1. And so if I want to multiply this, multiply this with a vector such that this leads to 0. So A minus 4i into x, I want this to be 0, and that you can just see that x equals 1 1 satisfies. I mean, if x equals 1 1 satisfies, obviously x equals 2 2 satisfies, and so on. Now for the other eigenvector, A minus 2i is 1 1 1 1. So all I have to do is A minus 2i of x equals 0 for x equals, this time make it 1 and minus 1. Okay, so that was a simple example where the eigenvectors could be easily found. Anyway, here is variation. Here is a variation of this matrix. Suppose I make up a matrix that is very closely related to A. So, say 0, 1, 1, 0. Then how is this related to A? B plus 3I equals A. Now, what is AX? B plus 3I x equal to lambda x plus 3x to lambda plus 3 times x. Now, here is something, I will leave it as a homework. Think about this. Eigenvectors of B is equal to eigenvectors of A. Try to argue why this is the case. So, I'll end with a few remarks. One has to be careful while making these arguments. So, suppose I have two matrices. Suppose Ax equals lambda 1 into x and Bx equals lambda 2 into x. Then can we claim A plus B into x equals lambda 1 plus lambda 2 into x? So, pause and think about this. Can I claim that if A has eigenvalue lambda 1 and B has eigenvalue lambda 2, can I really claim A plus B has eigenvalue lambda 1 plus lambda 2 with x as the eigenvector? The answer unfortunately is no, since the x's need not be the same for A and B. That is, you have A x 1 equals lambda 1 x 1 and B x 2 equals lambda 2 x 2 with x 1 not necessarily equal to x 2. The fact that we will see later is this. This is a fact that would end the discussion towards the end of the discussion about eigenvalue decomposition, which is following soon, is if you have a symmetric matrix, then has real eigenvalues. Now, to appreciate this fact, we should really see a matrix for which the eigenvalues are not real. And now, a matrix whose eigenvalues are not real. Here is that matrix. So, pause again, think about such a matrix. I am going to give out the solution. There are many such examples, but the simplest is this. And now, what is determinant of A minus lambda I is lambda square plus 1. So the eigenvalues are I and minus I. So, the eigenvalues are imaginary. Okay. Also, in the previous example, if you looked at the earlier example, we got two eigenvectors here, and these were the eigenvectors here are linearly independent. Now, this also may not always happen. So, I will give you an example for such a matrix. So, a matrix where we do not get independent eigenvectors. We get 2 independent eigenvectors. So let's take this matrix 3 1 0 3. You can see that, I mean, it's easy to see that lambda 1 equals lambda 2 equals 3. Now what is A minus lambda I, which is 0 1 0 0. So the only possible eigenvector which is non-trivial, x is 1 0, is the not get 2 independent eigenvectors. Our 2 cross 2 matrix is a eigenvector and there is no other eigenvector that is linearly independent of x. Okay, a quick summary before we end this lecture. So in this lecture we looked at the motivation for using eigenvalues and eigenvectors. By in particular, the idea is eigenvalues and eigenvectors help us understand the solutions to ordinary differential equations. We saw a concrete example. And then after defining eigenvalues and eigenvectors, we saw that calculating eigenvalues amounts to solving solving an equation which is called the characteristic polynomial, which comes as a result of calculating the determinant of a matrix. Given a matrix A, you solve A minus lambda I, the determinant of that equal to 0, and that's the characteristic equation. And we also understood what is the trace of a matrix and also the determinant of a matrix in relation to the eigenvalues. Now in the follow-up lectures, in the next lecture we'll be looking at how many eigenvectors, independent eigenvectors I can get for a matrix. If I have enough eigenvectors, can I diagonalize the matrix? So this notion of diagonalization is strongly related to how many linearly independent eigenvectors I can get for that matrix. If I get enough, which is the here NF is the number of columns of that matrix. So if A is an n cross n matrix, and if I get n linear independent eigenvectors, then A is diagonalizable. So this is an important idea that will come up in the next lecture.